I is not the square root of -1. It's actually a set of polynomials. This set is the formal definition of I. Of course, we can think of I as being the root of -1. This casual definition works for calculations, but you wouldn't want to be caught using it at a fancy dinner party. It's kind of like how the casual 4 is just this amount of objects, but the formal 4 is a squiggle monster. Formality is tedious and annoying. Oh, there's more in the back. But these formal definitions are important, because A, they set a standard that allows for clear communication. 2, they often make generalization easier, so we can explore new ideas. And finally, they're interesting. It's a lot more fun to think about math than about that itch that you have that just won't go away. So let's see why I is defined using polynomials. It all comes down to modular arithmetic. The typical example of this is a clock. 1 o'clock is the same as 13 o'clock, because a 12-hour interval returns the clock to the same spot. 12 hours equals 0 hours from the clock's perspective. It's like Sisyphus, forever spinning, trying to find some new 13th number, but always returning back to this. So this is the casual definition for arithmetic mod 12. It works for calculations, like starting at 10 and then adding 7 hours, we get 17. Nothing changes if we subtract 0, and 0 is the same as 12, so we end up with 5. 5 o'clock is 7 hours after 10. But it's weird that this addition problem has the answer 5, and also 17, and also 29, and also line 7. If we want to be formal, there should only be one answer, so that addition functions properly. And that one answer is all the answers! Just squish them together between some squiggles. It's the set of all 5 plus a dozen k. To do the whole problem formally, we take the set of 10 plus a dozen m, and the set of 7 plus a dozen n. We add together all possible pairs of elements, then do a little alge, and we end up with the set of 5 plus a dozen k. We get a different result if we use a baker's dozen, or a faker's dozen, or a Quaker's dozen. We can use any integer for the modulus. And it's not just the modulus that can change, but also the system. Instead of using integers mod a, we can use the polynomials mod a. So with a dozen as the modulus, let's add 10 and 7. Instead of being 17 plus a dozen k, where k is an integer, we now have 17 plus a dozen p of x, where p of x is a gnome. So this could be 12x plus 17, or 24x cubed line 7, or simply 5. And here's where it gets really fun. Since the system is gnomes, we can change the modulus to a gnome, like x. So now 10 plus 7 equals 17 plus x times a gnome. And now notice, these terms will always involve an x. They can't be constant. So the constant will always be 17. The casual definition is to set the modulus equal to 0. X is 0, so for any gnome, all the x terms zero out, and we're left with just the constant. The polynomials mod x are an unnecessary and overcomplicated version of the constants. But that's okay. That's what this channel is all about. Things do get better with a different modulus, like x squared plus 1. The casual definition sets this equal to 0, meaning that x squares to line 1. It's just like the imaginary I. The gnomes mod x squared plus 1 are the same system as the complex numbers. I corresponds to x, or formally, the set of all x plus the modulus times a gnome. And something similar goes for any complex number. A plus b corresponds to the set of a plus books plus modulus times gnome. The complex numbers are secretly just infinite sets of polynomials. And now you may remember, earlier in the video, I said that formal definitions often make generalization easier. We can generalize beyond, hey, turn it off! I just wanted the one sentence. We can generalize beyond the complex numbers. In my last video, we explored recursive complex numbers, where I squares to line I instead of line 1. We can construct this as the gnomes mod x squared plus x. The casual definition sets the modulus to 0, and we get the desired behavior. Last time we also explored more general complex numbers, where I squares to any a plus b. This can also be done with modular gnomes, using x squared line books line a as the modulus. This general modulus allows x to have any square. But we can generalize even further. What if we use x cubed plus 1 as the modulus? Casually, we set it to 0, meaning that x cubes to line 1. It's like I, but with a cube. They're the cubic complex numbers. And this cube means that the system is 3D. So of course, let's make a 3D graph. We'll use this spinning gnome grid as the input, where color represents the input's x coefficient. Watch what happens when we square all of the gnomes, and then when we cube them, and then the 4th power and the 5th. We can also take the sine of the spinning gnome grid, or the cosine, or the tangent. These graphs are pretty cool. So why isn't this 3D system a more popular field of math? Well, because it's not a field of math. A field is a system where you can divide by anything, except for 0. So the real numbers are a field. We can divide by any non-zero real. But the integers are not, since 1 divided by 2 is not an integer. Fields are really important, especially for vectors and matrices. Most of Los Angeles relies on fields. So the complex numbers are great. They are a field, and maybe even the best one. But this 3D system is not. Division doesn't always work. For example, with x plus 1 over x plus 1. This should equal 1, but multiplying both sides by this gnome, we end up with x cubed plus 1 on the left. And that's the modulus, so it equals 0, meaning that the entire left foot side is 0. But the right foot side is not 0. It's not a multiple of the modulus. We've run into a problem. So why did this happen? Well, the casual definition sets the modulus equal to 0, but the modulus is composite. It can be factored into smaller gnomes. So we end up with these two non-zero gnomes that multiply to 0. This shouldn't happen in a field. We made the complex numbers using x squared plus 1. This gnome is prime. It doesn't really have any factors, so we don't get that 0 multiplication issue. When the modulus is prime, we get a field. And this is kind of unfortunate. It means that there are no higher dimension complex numbers. If we define I using a power above 2, we won't get a field, because the corresponding gnome will be composite, having some factorization. Although, notice that this factorization uses root 2, which is irrational. So far, I've assumed that these gnomes are real, but if we switch the system to the rash gnomes, then this factorization doesn't work. X to the 4th plus 1 is a rash gnome prime, which means this is a field. We can make a 4-dimensional complex field, it just won't be continuous. And the same is true for any power of 2. X to any 2 to the n plus 1 is a rash gnome prime, so we can make a 2 to the n dimensional complex field. Bonus points for the first person to leave a comment explaining why, and slowness points for the last person to leave a comment explaining why. And thanks to my supporters. They help to fund the channel, especially since I refuse to use mid-roll ads. If you want to learn more about the weird world of prime polynomials, check out my video about them. And of course, thanks for watching to the end. Well, I guess we're not quite at the end. There are still a few seconds left. But I can't say thank you after the video has ended. You wouldn't be able to hear it. I really should have just said